Hello, everyone.
Hello.
All right, welcome to ITS or Tech 581 or ITS 531, 581, whatever it is. It's technically supposed to be ITS 530. All right, so welcome to the class. As you know, today we're just going to do the presentations. We're really going to do this on a first come, first serve basis. And I'm going, I really don't have any announcements instead, except to say that I want to remind you that the final exam is next week. Okay, please don't forget about the exam. This time it'll be a written exam. There's no time for a practical exam. Post the grades kind of right away. So please just don't forget that. So that's all you have left. You have the final exam, in a week, next week. And today you have your presentations. There was no homework assignment from last week. So what you will do today is do your presentation. You have about 20 to 30 minutes and kind of discuss the problem. And then after that, we're going to open it up to questions from everyone. Remember that these sessions are being recorded, and I'll post these on YouTube at the end of today. And I believe, and also the last thing is, I will create a Dropbox for this project so that you can submit all of your files on there and a report. Okay, so that we have that. Okay, so at this point, before we get started, are there any questions? No questions, it seems. Okay, so I think everyone is here. Hopefully everyone is. Okay, is there anyone that would like to go first?
I can go first. I don't know.
Excellent. Okay, David, please go ahead.
So I'm going to share my screen, right?
Yeah, you'll need to share your screens and then just talk. Give a talk about the topic, and then after that, we'll do questions.
Can you see it?
Yes.
Okay. So I didn't really, I know in class, when we were still having classes in person, I know that a lot of people had projects from like stuff they've done before or like interesting topics that they were interested in. I didn't really have any specific things that I could think of to make my projects with. So I just looked on Kaggle for data sets, and then I just played around with a few different problems. So I just, instead of having one really cool project, I have a couple that I played with, and they all work pretty well, except for a few of the RNN ones. So I'm just going to go through each and kind of explain what I did there. So first I did, is it black for you guys over here? I have a black bar and I don't know why.
No.
There's like a black bar. Okay, then it's just on my screen. So I did two CNN projects, and they are both kind of similar to what we did for or for what I did for my midterm. So I still use, or I use the same Kaggle data set, but for the midterm, I had the data set that we used in class was the data set that I used for my midterm. So in that midterm, I used fruit that was really different. So I had, I think, bananas and apples. So one is long and yellow, and the other one is brown and red. So in here, I tried to make a data set that has fruit that all look almost the same. So I have a ton of classes that are just different sorts of apples, different kinds of apples. And so that's all the apples. And I have cherries, which also kind of look the same. Then I had clementine, which is probably one of the ones that's not all that same. Then I had strawberries, which also, yeah, they're not brown, but still they're red. And then I had the tomatoes that were in that data set, which they had a ton of. So I just thought that's kind of interesting just to see how well the CNN is going to perform if the data we're giving it is not that easy to distinguish. So I did that, and it actually did much better than I thought. So my laptop's not very strong, so it usually when I run those experiments, it sometimes just kind of overheats and just shuts down. So I never really have the time to let them run all the way to the end. But when I had that and I ran it, I gave it, I think like an hour. I let it run because at some point I just have to stop it before it shuts down, because when it shuts down, all my data's lost. So in this case, I just had it run for 18,000 generations, and we can already see that it's almost perfect already. So we have a few mistakes here and there. So there's one that's wrong. There are a couple. But even though all the fruits, and even just for the apples, which, I mean, even if I just look at them, to me, at least at first glance, they look almost the same. But after training, the test data set, performs almost perfectly. And so after 18,000 generations, I had a F measure of 0.995, which, like I said, is much higher than I thought. And that is without really having to change much on the code from what I did for the midterm. So I really just kind of used the midterm code for that one with a few changes here and there. And then I had another.
So that was a convolutional neural network?
Yeah, that's a CNN.
Okay.
And then I had a second data set that I ran with CNNs. And that is, again, a bit different, because for the midterm, I decided to shrink down my data set so it's only 4 classes, because I thought the more classes, first, the bigger the data, and the longer it's going to run, because my computer is just going to have even more trouble handling all that data. And also because if there's more classes, there's more chances to do something wrong. So I had a data set where I have 31 different classes. The one we just had is only half the size. I think that one had 15. So here I have 31 different classes, and I ran that again. Now this one I couldn't run as long, because this one really crashed my computer a lot. But after 7,000 generations, we were already in the upper 90 ballpark. So I was happy with that. And we had a 0.95 F measure. And here the classes are a bit easier to distinguish, but since there's just such a large number of them, I just didn't really know what to expect, because we haven't really, or at least I haven't really handled such big data sets before in terms of the amount of classes. But I think if my computer would be a bit better, I could let this run until it hits 100, I believe. And I think the same would have also been true for this one. So like I said, both of those work really well, probably better than I thought at first. And those were also not that much work, because they just worked pretty well out of the box straight away. So then I looked at a few RNN problems. So this is similar to what we did for the homework, the last one. And because I think so that was the text for the homework. It was pretty short. So I just wanted to see how this all works if I use something that's a little bit longer and a little bit more complex. So I used 3 different things. So for one, this one is the one from the ones that I had that performed the best. This is just the name of all the episodes of Star Trek from the first series, so the first 3 seasons, all the episode names. And this one, I believe I have it somewhere here. This one also performed in up until like 90-ish% almost, which out of the ones that I did is the best, because this one's still, it's not that much longer, it's not that much more complex than the one that we had, and it's very well structured. So I think that kind of helped. So after that, I used the first chapter out of the Harry Potter books, which is just a lot longer and a lot more complex. And with this one, the RNN did struggle. It never really got anywhere great. I think, again, if I would have something in there that would be, or if I had a computer that's more powerful, I think if I give it more time to actually train, it would get better, because at points it did go into like the 30s, I think. But overall, this one was the worst out of them all, the ones that I did. And I believe that is because I kept I kept it at 50,000 iterations, and I think this one just needs a lot more, I believe. So if I might, after tonight I might
Did
just.
you by any chance print out the vocabulary size?
I still have the code here.
Yeah, because if you think about it, that's going to have more words, correct? Because
Yeah.
anything that's larger will involve more things that you have said, more unique things that you have said. So
Right. Yeah.
your
So for this one, I
size.
kept it the same for now, but I'm planning on working a bit more in this one because I mean it just did really poorly.
No, and
So
what I'm saying is if you have a larger vocabulary size, the probability that you're going to say a unique word goes up.
Right.
That's
Yeah.
why your performance is not good. I think you would need more time.
Right. Yeah, but I will probably try that maybe after class is over tonight or even after I hand it in. I'm just going to see if I can get this to perform a bit better. And then I did one more. This is just an article that I have, and this one again, just what the professor just told us. It also has a lot more unique words. It's not as long, and we can see that this did a lot better. We even got into higher numbers in here, even though that might just have been a fluke. But this one, I think I wouldn't have to change that much. It's really just, I think this one is on the right track, whereas the Harry Potter one, I really think is just kind of far off and still needs a lot more work, whereas this one is doing pretty okay. I still would have had to do a few more things here and there. But I think, yeah, I think the approach for this one is right, whereas for the Harry Potter, like Professor Calix just said, that one, I just have to change a few more things, I would say. But yeah, just since I didn't have any great ideas, I just kind of tested a few and just tried which one works best. And the CNNs, like I said before, they do work a lot better than I had thought. And for the RNNs, yeah, I just have to work a bit more on them.
Well, that's a good conclusion to have because CNNs are definitely one of the most powerful and most well-proven of all the deep learning techniques, I think. They have, they were the ones that I think I told you the story that in 2012 were really the game changer. First ones. RNNs, as I said, I think with you could see that the accuracies were just not picking up.
Yeah.
So you definitely want to leave that running. And I think eventually, once it's, the fact is it's like a explosive problem, right? You have so many combinations now of these n-grams because of the larger vocabulary size. I'm guessing your vocabulary size is a lot larger, and that obviously would create problems. But it's a very good finding and observation. So great job.
Thank you.
Anything else, David, that you want to present?
No, if there's no question, I'm going to stop the screen share now.
Guys, any questions for David? Go ahead.
Okay, I'll stop the screen share now.
Okay. Okay, so there are no questions. All right, thank you very much. Great job. So virtual clapping here. Great, there you go. Okay, who wants to go next?
I can go next, Professor.
Umendra? Okay, great.
Yeah.
All right, thank you. Go ahead, please.
Okay, everyone can see my screen?
Yep.
Okay. So this is the project I was working in. So trying to build an autoencoder. It's learn the network behaviors like that based on the pattern of the traffic. So we are planning to use the same approach for different other network-based services. Like there are like different application layer services. Similarly, we are planning to work the same with like for the intrusion detection kind of like malware detection, anomalies detection. Similarly, we're going to use the same approach for IoT. So this is a very preliminary phase where I'm just testing with the model and try to see like how much accuracy or how much we can get closer to predict there is some kind of a difference in the packet. So this is something related with an autoencoder for the network packet. So let's go on the very in brief with the my approach. So I've collected network packets on a controlled environment, we can say like that. So um, so these packets are all captured in PCAT file. So these files are all collected over a period of time, and I use different other approaches, softwares like NTOP in order to identify the layer 7 protocol within those packets which are captured. Similarly, there are like 80 plus features when I extracted these features from those PCAP file packets. And the model that I'm working right now, it's only like 2 hidden layer. So, but I think I get somewhat really close to the one that I tried earlier. And so if I talk about the dataset features, I have 83 different features, which are all based on the network packet behavior, the flow of the traffic. So most of them are basically the standard deviation, mean, the burst size, and some of them are basically related with the very normal like packet layer information, such as like the IP address, the source and the destination IP address, obviously, the flow pattern, the protocol they use, the layer information they have. So there are basic packet information in the features as well. And the most of them are basically the flow of the traffic. Similarly, I used NTOP in order to classify the layer 7, that is the application layer protocol in these packets, and try to tag all these packets based on the source port and the destination port based on the flow of the network packets as well. So based on that, I just listed all those packets within that specific protocol. And then I used a bin approach where I talked with Professor Calix as well. Like he told me like it will be better approach if you will try to make different bins for different protocols and then try to incorporate with an autoencoder and try to see like whether we will be able to identify the difference between uh, the the normal versus abnormal. That was like something that we are trying to achieve. But right now, the one that I've tested is between different layers, the protocol services, whether it's a uh, web-based services or it's anything else than the web-based services. And that's, I'm trying to identify like how much difference they are in terms of a network behavior within their own service type, so service protocol. So that's what I'm testing in my autoencoder. So my autoencoder architecture, it's in 2 hidden layer network. So the layer 1, so input is 84, that's all the features I have. So the layer 1 is 62 neurons, and then the layer 2 is 31, and leading to the output again for 84. Here's the inference function. So the inference function is pretty much similar that professor shared with us. I just used the TensorFlow random uniform function and just added one more additional layer in it. And then I tried different approaches on this one. So I think layer 2 gave me the better output compared to the other one. So I will share some trial and error screenshot as well after this one. So here we have. So the very first one I tried with the scaled input. So I scaled all those features and then try to train my autoencoder and can try to calculate the distance between the same. And when I tried with any scale, the output was pretty unpredictable. See the difference, the distance between the input and output is, the predicted is pretty high. So the input data and the output data is same, but the predicted input, the predicted output and the input data, there is a huge difference. So that doesn't make sense to me. So then I tried not to scale the data, because when I try to print out the, because of
Sumendra, I'm sorry. Can you explain that a little bit more for everyone? I think this is a pretty important part that what you're
the
discussing.
scaled one, right, Professor? The scaled and the standard input.
Not the scaled so much. I think everyone would understand that you're scaling the data in one and not in the other. But I think that those bottom screenshots where it says distance between input and output.
Yeah. So
Explain
distance
a little bit
between
more for
yeah,
everyone.
the here I'm comparing with the same input size, like same the input. If it is an HTTP packet bin, then I'm feeding input as an HTTP, and the output would be same. So there is no change in between input and output. So there is no difference in the first distance, because we are not learning anything. We're just comparing the input and the output. Basically, input and output is the same feature data set. So the second one is the predicted output is after we train our data set, that goes through our inference function. And then when we try to match the input that we give and the learned output, so there was a difference. So, and this difference was especially with the scale. And I tried different level of hidden layers, like hidden layer 1. So even I add any hidden, like more hidden layer, it doesn't change the output. The difference was pretty much similar. I guess the one that I have right now is pretty low, because normally it was in 700 range earlier. So then what I did is I didn't scale the input. I just um, supply, like I just feed whatever I have in my data set, because I have already pre-processed my data set. So there was no trouble in feeding the data. So when I feed it, then I see the difference was pretty low now. So that was in the 500 range, and this is in the 2. So it makes pretty much convincing for me. And then afterwards what I did is, like, I just feed whatever data I have that is pre-processed by me. I use Panda to just separate them into bin and convert the data type, because flow and the traffic flow ID and IP address, timestamp, they are in different formats. So I have to make changes in them. So actually the data is pretty much ready when I try to fit into my model. But I was using the scale to see, like, it might give more better result. But the one that I have, like, was more accurate. So all of these output are based on like 50,000 epochs of learning. So here are some of my results. So these are different autoencoder which I trained based on different protocol that I just created in a different beans. So the very first one is the HTTP packet versus the Google. So they both uses the same approaches of communication, but as we train our model, we can see there is a difference. So the input and the output, when I feed it initially, so there was a difference, because the difference between the HTTP packet and the Google packet is different. But when I trained it, the distance became low, as we can see, because I'm using the random uniform function. So It is it's similar the one that we use for denoise, and it try to uh, make like we try to reduce the noise in the data, and that's what we are doing. As we move further, we can see the higher the difference, the lower the rate. It's just working in a vice versa manner, but I don't know, like we might have to like I still need to figure out some more work on it. And as much closer, um, the difference is like pretty low. So here the Google and HTTP, we can see there is a pretty good amount of difference between the predicted and the real input. And similarly, the SSL and the HTTP, so they work on a same um, like the protocol. But the only difference is the SSL is the secure socket layer, which runs in layer 3 in the network layer. So this is something related with the web server itself. So you can see there is very little difference in between the input and the output. And similarly, I tried something with the Skype, that is something related with the video and the chatting, and the HTTP. But when I try to train my model, I see they are almost very similar. So the gap is pretty low. So the more sparse I think, the more closer they became. That's what I'm seeing from my test.
Can I ask you a question?
Yes, Professor.
Okay, so let's say, for instance, that Skype versus HTTP. That autoencoder, was it trained on purely Skype packets or pure HTTP packets?
The first one is the one that I'm trained, Professor. Skype was the train.
Okay,
The autoencoder is
so
trained.
this is, I think, the one thing that is not clear from your presentation. So I don't know if students are getting this. So you build an we looked at simple autoencoders and denoising autoencoders in the course. So the students should understand that. So what you're saying, you want to, and when you do the presentation, because you'll do this presentation several times actually. So you train this autoencoder with just one bin of data, which is the Skype data.
Yeah.
And then you held out a test set of maybe a few Skype packets and also this HTTP packet. And so you ran all of those test sets, which the autoencoder has never seen. You run them through the model, and then you get, it gets auto-encoded, right? So encoded and decoded, so reconstructed. And then what you do in those bottom little screenshots is that you calculate the distance between the input and the output.
Yes.
And so then you would expect, and this is my question to you, let's say that you had 10 held out Skypes and held out HTTPs that were not, that the Skypes were not in the autoencoder training. You ran those 20 through the autoencoder and got 20 outputs. You calculated the distances between the input and the output, and then remember, you have to rank them. That's
yeah, Professor. I got
they
your
have
point.
very little meaning, these distances, but they
Professor.
meaning together as part of a ranking process. And then what is your result if you do the ranking? You know what I mean, Sumendra?
Yeah, Professor, I got your point. So right now what I have done
Make
is...
sure you convey that with this. Okay, thanks.
Okay, Professor. So right now what I'm doing is like, I trained the one which is the autoencoder, like Skype is the one in the first, right? So that means my autoencoder is trained within Skype packets. So I feed in the HTTP packet now. And this is entirely an HTTP packet. There is nothing mixed. I didn't combine, I didn't mix anything because I didn't build any ranking system where I can like fit in like 3 to 4 different or like multiple different bins in same and then rank them accordingly. This is entirely an individual. So I trained my autoencoder right now at this point that the autoencoder is trained with this specific protocol, and then it is specialized to know for that specific protocol, and then I pass the bin from the different one which is completely different from it. So it's all with the HTTP or it's all with the Google. So if my autoencoder is trained on Skype, and then I feed something different than the Skype in order to find out like whether it can find any difference or not, or if there is any difference, what's the what's the difference in between those two different protocols. So that's how all these results are built in. So I use different approaches over here and then try to find out like um, different protocol with like less similarity and more like they are like more in similar. So if you see the result in over here in the back, so I use SSL and HTTP. So the distance that I calculated with the actual input, the distance between them is 6.20. So after I train my autoencoder on SSL packet, and then I test my data set, a validated data set is an HTTP, then the predicted outputs were 5.66. So there is a very less difference in that, which somehow relates to me that both of these protocols are almost using the same network behavior pattern.
So let me interject here, because actually I think Sumendra has a very interesting finding there, and I just have a slight, a different interpretation of that. And you guys, let's discuss. So this goes back to that example that I've always given you of training a model to learn to paint like a Picasso. You remember that, I've given that analogy quite a bit. And then you guys take a picture of your family, you run it through the model. What do you expect that would happen to that picture?
Try to make it to the one that we trained.
Right, it'll try to make it more of a Picasso, right? In theory, at least to the computer, maybe not to our eye, but to the computer, it'll try to do that. I believe, actually, if I understood you correctly, that's what's happening here. You have a model that you trained to be SSL.
Mm-hmm.
You gave it, you trained it. Then you gave it an HTTP packet, right?
Yeah.
And you're saying, so what I didn't understand there is what is input and output here? Because those two, for it to be a distance, they can't be the same, correct?
Yeah, they are not same, Professor.
So what are they?
Input is SSL and the output is HTTP at the very initial phase.
Okay, that makes sense. So let me ask you this question. Input data is SSL.
Mm-hmm.
Output data is the HTTP without, as it is.
No, not as it is. I trained my model with an SSL, and then I feed my output to validate that output is the HTTP now. So I feed it there, and
Wait,
then
so that's what I'm a little bit confused here. Input data is what?
SSL.
It's an SSL packet.
Yeah.
What is output data?
Output data is HTTP.
Okay, all right, that's what I was saying. So you take from the bin an SSL packet and you take your held out HTTP packet, you compare them, correct?
Yeah.
Okay, now in the next one, what is input data?
Is SSL.
The same SSL that we used before.
Yeah, the input.
Okay, what is predicted output?
The predicted output is I feed output data in there. That is an HTTP, and it trains. It goes.
Okay, yeah, I think right. So let me put it this way. Let's just use letters. Let's see if this works. You feed it X.
Mm-hmm.
No, input data is X. Output data is Y. They have the same dimensions, of course, but you measure the distance. One is SSL, one is HTTP, right?
Yes.
So
right.
Then in the next one, input data is still X.
Mm-hmm.
And predicted output is going to be, let's call it M, where M is Y, but that goes through the model,
Yeah.
right?
The train model.
So what happened is you fed this time you took output data, you fed it through it was fed through your model, and now it has been modified. So it's going to be that original Y modified by the model to give you M. And now you compare M to X. So
Yeah.
whereas before X and Y were very different, now you have X and M has been made a little bit more into the SSL type. That's what the model does. So that goes back to what I was saying about Picasso. If you, let's say that you had trained a model to become a Picasso, what it did is initially you had, you know, Picasso and your picture. You compared it. The distance is quite pronounced. Then you take a Picasso and your picture through your model. Now your picture has been made into more of a Picasso, and so the distance is less. Do you understand?
Yes, Professor. The higher the difference, the higher the distance, like the similarity, the difference.
That's right. But I believe, given what we're discussing here, that's what if you're saying that 6 is higher distance than 5, it's the semantic meaning of that in terms of distances is that the two bottom ones are closer together, which means somehow in the features they're a little bit more similar.
Yes.
So that, you know, that's a good you've proven that the autoencoder in fact does that, right? It transforms your image into more of that model.
Yes, Professor. Because the inference token that I'm using is the uniform, random uniform, Professor. So it's a denoise, the same. It's try to make similar. It try to make remove the whatever it's learned. It try to remove the noise and try to make it similar to the input, and that's what it's doing.
Right. I think the whole mechanics of this are good. I just think you would have to probably, let's say you have, as I said, you built a model on SSLs. You already proved that it's gonna try to make them into SSL. That's what that little bottom screenshot seems to be telling us.
Yeah.
So what you would need to do now is in the held out test set, right?
Mm-hmm.
You understand? You'd have 10 SSLs and 10 HTTPs. You run them through the model and you compare the original to the transformed.
Okay.
So really you want to compare not input data to output data or input data to predicted output data, but I think you want to compare output data to predicted output data.
Yeah, I can do that. Yeah.
You understand? Because what you're doing is, you know, this actually was a very good little conclusion. What you want to do is you want to feed a vector into the model, and if it's already a Picasso, it's going to look like a Picasso on the coming out end.
Mm-hmm.
But if it's not a Picasso, let's say it's Norman Rockwell, right? It's gonna run through the model, and the model will make that Norman Rockwell into kind of a Picasso, but it's still not as close to a Picasso as original Picassos are. And so that's why I was saying if you have a test set of 10 SSLs and 10 HTTPs, hopefully in the distances, it'll be reflected, right? That the SSLs have a closer distance than the HTTPs, which will be a little bit different, which I think, you know, it's kind of the same idea of what you have in that bottom.
Yeah, I just need to add one more and then just compare the output data.
But do you understand, Sumendra?
Yeah, I got your point, Professor. Yeah.
Okay, I'll stop now and please continue.
So, yeah, so I was sharing like the difference that I was getting, the closer the features they share, the closer the distance become, and the worse the difference of the features, the difference become higher. So you will see the difference if the sky in the HTTP they almost share the same kind of features. So the similarities is almost the same. Similarly, the Windows update versus the Google, there is a little difference in them, but not as much as compared to the HTTP and Google, where we have a lot of difference in there. So this is what I found out till now, but still there is a lot of work to be done because it's still not a perfect model. It's still training and still trying to understand like what other inference function we can use, still trying to use the CNN models and then try to see like how they perform on it. So this, so I came to one conclusion that scaling is really not that important depending on the data type that we are using, because in my data, there are lots of zeros and there are lots of exponential values, which doesn't make much difference when I try to normalize my data set. So when if you can see it, like when I try to do it within scale, the output, the difference was pretty high. But when
One thing that might make a difference, I think you're right. One thing that might make a difference more is the distance function. I don't know if you tried different ones.
different, yes, professor, that also makes change. Um, the one that I'm using right now is in cross entropy. I'm not using the least square mean. That so I use the cross entropy.
Right, but that's for the loss function, right? But I mean also when you measure the distance at the, you know, once you get the outputs.
Oh, that is the equivalent distance.
That's still Euclidean, right? You're still
Yeah.
that.
Yeah, professor, there are so many things that I really need
But
to.
there are others. There's Manhattan distance. I mean, there's lots of them. So
Yeah, there are lots of loss function also, professor, and
yes.
even like the inference function we can use different. So this is, I think it's really a vast problem because we have to go through different set, because there are a lot of set and we have to see like how we can fine tune our model. It's all about I think right now we have a data set, we have a working model, we know the data set works, and we can see that we can still come out with some output. So now the only difference that makes here is like which algorithms or which inference function, which loss function, and which distance functions will give us like more closer and more minute uh, outputs that we can make. Like, because when we try to do something with an anomaly detection, and I know like if there will be very minor difference between a normal packet and an abnormal packet, and then there will be only few features which might hold that distinct feedback. So at that point, I guess we need to be more accurate if we need to make our model more perfect. So now I think it's all about the inference function, the loss, and the distance vector that we use to calculate.
One thing I want to say about this is I think, you know, what's missing, I don't know if you have it in the last slides, but is the ranking. You're still not doing that.
I didn't do the ranking, professor, till now.
Remember, I think I get what you're saying, but it's important that you do the ranking because that's really what's going to give meaning to the distances. Remember, as we have discussed, we've said that we're, you know, you could build thousands of these bins and you have access to an entire data center, right, of a country. And so that means you're going to have billions of packets. And so there's no, this is like a classic IDS problem. The system administrator just cannot look at all the alerts. It's just not possible. But with the ranking system, every packet gets efficiently run through the bins, run through the autoencoder, and a distance is assigned to it. And so you don't have, if you have 100,000 packets that you ran and 100,000 have distances, you can't possibly look at all 100,000. But when you do the ranking, the most different will surface. And I'm not saying that's the end of the story, but I'm saying that's probably where you want to start in just, you know, think, as I said a couple of times, think of them as bubbles, right? There will be a lot under the ocean, but let's see what bubbles rise up first. You understand, Sumendra?
Yeah, I got that point, professor.
So it's very important, I think, that whenever you do this, that you have an independent, held out test set. Doesn't have to be thousands of things, as I said, 20 of each, 20 of that bin. So of packets of that bin, and then 20 different ones. And then you run them through this, all 40, rank them. Hopefully, the ones that are not of that bin are going to be the ones that surface to the top. That's really, I think, what the one thing so you've done a lot of great things here. We still need to prove if that works. We know it, we believe in theory it'll work, but don't see it here in the slides.
Yeah, I didn't rank it yet because I do have a set where I just mixed different a protocol, and I was trying to do the same, but I didn't still because there are lots of trial and error that I was doing because of the accuracy that I was suffering with the distance, because there was like a lot of distance when I was doing calculating with different, like the first thing is the scale itself make me confused. And so yeah, it was a whole new learning process for me because it's a trial and error, because even I don't know how it's, the output gonna predict. So I came to know that like when I was doing the trial, and then I came to know like if I do any scaling, it doesn't make sense for, because of the way, the nature of the data set. So I just feed it as it is, and then I try to see the difference, and then I was just trying with the different protocol, and then try to calculate and see the distance, how they are performing, like in what sense there is a difference. So I think I can add ranking. That's not a big thing right now, Professor, because the thing is uh, whether it's working or not, that's what I was giving it a try. And whether the output, whatever we got, it does make sense. So yeah, I know like you already talked about it, like ranking is the one, because at the end we need to have a result. So based on all this calculation, we need to sort out all those anomalies, or all those abnormal, the one which is like more abnormal on the top, so that they can be ranked uh, as an abnormal packet, where a network administrator, they can look into those packets and then try to find out like, is any intrusion or any abnormality, or it's just any other normal packet. So yeah, but I didn't added the rank over here in this one. So just I showed the difference between different protocol, and the difference and the distance within them. So that's what I did. I did with different other protocols, and that's what it is. I didn't add a ranking. Yeah, I need to add rank because this thing is still need to be worked on. So this is my project too. So I will be working on it with the other, because I did this one with the application layer data. So there are still other data set that I need to perform. So yeah, the ranking system I definitely need to add.
All right, great. Anything else? Any questions from the audience? No questions? You're all pretty quiet. Okay, great job, Sumendra,
Thank you, Professor.
seeing that ranking part.
Yeah, I will add that ranking part for sure.
Okay. And we have something, I think at this point, once you have that ranking, we have something that we can try to publish. So that's the great thing about it. Okay?
Yeah, Professor, I will add.
All right, so we'll talk about that. Okay. Who would like to go next?
This is Joe. I'll go next with Drew.
Oh, thank you, Joe. Okay, go ahead.
Okay. I'm trying to share my screen. I'm not sure if you can see it.
Not yet.
Okay. So hopefully you'll see something.
Yeah, we see it now, I think.
Okay, so
Yeah,
I worked on this project with Drew Johnson, and he's hopefully he'll chime in as well.
Yeah, I'm here.
Yeah, great. So it's just a simple auto encoder application that we did. So I work for a stock trading firm, and we just clear stock trades. So basically, when a trading firm makes a trade, they send out information in two places. They send it to the exchange where the actual trade's taking place, and then they send a copy of the exchange to my company. And what we do is basically at the end of the day, we're a bunch of accountants, and we make sure that you can cover all your trades. You have enough equity, basically money, to cover all your buys and sells and whatever you hold on to during the day. So at the end of the day, we just make sure that you're able to afford the trades that you made, and basically say, like, we've seen some of our customers lately just go out of business because they couldn't cover. So what our project does is during high volume trade days, we need to add extra resources into our environment, spin up some HVs to handle the hand up virtual machines to handle the extra processing. So give us some extra processing. So I need to basically detect anomalies when data is coming in. So we'll see the higher trade volume. So based on higher trade volumes would be the amount of trades coming in, the influx, per hour or per minute number of trades. And then also we need to look at how much they're trading as well. So we'll know if it's a high volume day, let's say an average firm does, let's say 500 lots of whatever trade a day, and all of a sudden they're trading 10,000. So that indicates to us that's going to be a high volume day because there's something in the market that's causing volatility. So we need to just be able to detect that. So that's what this application does. It just detects anomalies. So it's an autoencoder. So here's a sample of the data that we would typically see coming in. There's might be some more, but we usually get like a trade date. So the autoencoder, it's a date timestamp coming in. A put or call, that's just basically a buy or a sell. And then you get the long quantity. So that's the amount. So they're going to long a stock. That means they're going to hold on to it for a while. So that's the quantity that they're moving in, and then the long price, what they're paying, or what they paid on the trade when they locked it in. Then there's the short quantity, and then the short price. So short quantity means it's basically a short sell. So it's a short-term thing that they're going to hold on to the stock and then replace it if you know how shorts work. The price, and then there's usually a symbol associated with it. So what I did, I couldn't use real trade data, so I created a C# application that just generates random data and just put some parameters in there so we can show the different variances and sort of detect anomalies. I was going to run the application. I know some other people just did. So it's going through it. It's reading the data. And then, I don't know, did you want to talk about this graph, Drew, or?
Yeah, so basically what these graphs, it just helps how the data is normalized, how it, basically the train, and then there's another one that will just show the testing frequency as well as soon as you close it out. It's basically just showing how it's how the data is normalized.
Okay, I'm gonna run then. So it's using Keras LTSM, going through. Then it's going to train on the samples. It runs fairly quickly. So here's our ReLU, right? So it's just showing our model loss, and you can see how the training data and the validation are similar.
Yeah, it stabilizes there, and then this is just the distribution of it, basically. Another chart showing roughly same thing. And then these charts basically help with seeing exactly when they're detected, how there's a couple of these charts basically showing where the anomalies are detected, how they're detected, when we would actually need to have extra resources for his company to be able to do it.
Okay. So see here inside the code, it's looking for anomalies. So it's going through and it's basically using starts out as a Panda data frame, and then goes through and puts it into a training set. So I can show the code, but it's actually looking to see when the anomalies were detected. So when anomalies detected, here it just shows anomaly. just prints it to the screen. But in actuality, we may want something to occur, like send an email, or if we could figure out a automated way, which I have to talk to the ops guys, how to spawn or fork a virtual machine to spin up on its own. I mean, that'd be the ideal situation.
Yeah, and then this little slash chart is kind of the easiest to, in my opinion, to see like exactly when an anomaly detected, when something actually needs to take it is, the red line is the threshold of, this is when we actually need to take charge or something. We need to do something after, something's going on that, all this stuff is happening above the red line. So this is when we actually need to take action.
I can move in some of the code. So basically, it goes through using a data frame, and then once we find our anomalies, we put it into a tensor, and we just go through and we just go in there and just finding the anomaly, like I said, and then putting it into a screen. And there's some trend analysis. So if we notice anomalies going for greater than 4, so on your 5th one, then that's when you want to take action, because sometimes you may have some anomalies. It could just be some one-offs or edge cases where something's happening, but it may not be a high trial volume day. So for whatever reason, a brokerage firm might be just selling off stock. So if we see things that occur, more than 4 times, so 5 or more, then we're seeing a trend and need to just take some action on it. That's basically it. I don't know if there's any questions or.
Yeah.
Expand on.
Great job. I have a couple of questions. So you said that it's an autoencoder, but then you also mentioned that it's an RNN. So can you?
Oh, I'm sorry. RNN is what I wanted to do. So it's just an autoencoder. I'm sorry.
Oh, okay.
Yeah, RNN was something we messed with and we wanted to eventually get, but yeah.
Oh, okay. Maybe I misunderstood. Okay.
Yeah, I shouldn't have said that. We were trying to get this to work as an RNN, and it didn't work out the way
Right.
we wanted it to.
And RNN makes sense because this is time data, and so you kind of want to have that idea of what was the previous 3 trades, and then maybe there's a pattern there. So I can see that.
Yeah, we sort of got that here, and we were working on the code and we just ran out of time.
Right, and that's great. And that can be actually something for you to consider for the future. So you did an autoencoder, okay? So that's great. Autoencoders are extremely powerful. As you saw, Sumendra's project is also an autoencoder because it's unsupervised.
Yeah.
So you're telling me, if I understood correctly, how many of these simulated data samples did you have in your data set? Roughly?
A couple thousand. I could include the Excel CSV with it.
And then so you ran those into the autoencoder and then created the model. And I saw you had a function there, predict, with Keras there. And so you took then all the 2,000 samples again, ran them through the autoencoder. How did you figure out how dissimilar they were to the model? Where did you calculate a distance function?
Right here. What are we doing? So I just looked at the score. This basically right here told me if it was an anomaly. So this is basically a Boolean function. So yeah, we scored a loss and then a threshold.
Right. So yeah, that's pretty obvious. So if scored greater than a threshold, it's an anomaly. So it's some kind of a distance function right there.
Yeah.
You know where that's calculated? Where exactly?
See.
Get there. I see it. So it's that line where the absolute value is. You have NP absolute X pred minus X test. You're probably just doing that for the whole matrix, I'm assuming. And
yes.
it gives you that's probably where it's happening. Okay, so great. So that's what I wanted to confirm. So there's a distance function there. Okay, yeah, it's pretty straightforward autoencoder. You give it the data, build a model, it's very similar to what Sumendra's idea is, as you can see the versatility of an autoencoder, right? So Sumendra's applying it to what is it? Now, intrusion detection or anomaly detection for network security. You're applying it to finance. Interesting. You might consider doing what he's doing with breaking things up into bins. Just that makes more homogeneous autoencoders. You can, fully automate them. So that's something to consider. Let's see. Do you have where you built the model, the inference function on this? Just want to take a look at the architecture if you haven't.
Let me see.
I know you did it through Keras, but it's still there. It's probably that.
Yeah, here, I mean, so I build the models.
Okay.
Keras were just easier to work with.
No, and I get that. You guys will use Keras from time to time. So. Okay. All right, that's fine. Great. So now, did you measure performance in some way to make sure that it was accurate, what it was doing?
I guess when we just off the diagrams.
Off the diagrams, you were convinced that the transactions you saw marked as anomalies were in fact anomalies.
Yeah, because I visually looked at the data and how it lined up with the graph. I see where you're going with your question. Okay.
All right. That's what you want to prove, right? That it's giving you actually meaningful data. Okay. And you can prove that by you can, yeah, the graphs, I guess, does it. Okay. All right. Good. I don't have any more questions. I think it's all clear for me. Everyone else, are there any questions on Joe's and Drew's project of stock trading? If you solve this algorithm, you'll become the next Warren Buffett. Any questions? Okay, great. So great presentation so far. I guess there's no more questions on their project. So who would like to volunteer to go next?
Yeah, I would like, Professor.
Okay, great. Go ahead, Yang Yang, please.
So mine is pretty simple. It's just the CNN terminal, and I got all this data from Cargo. This is the partial of the original data, and on the left part is the picture labeled as no terminal, and on the right is, yes, you can see the terminal in these pictures. Yeah, you should see it. And the code I use is just from the Professor Calix, and the only part I modified is the weight and bias part. The code I got from the Professor Calix is not working for me. I mean, the result is not seems learning. It's always the same result. So I did some change on it. I changed it to the TensorFlow.channel normal weight shape, and then is the standard deviation. And this is my convolution layer. You can see there's two layers, and the input, the shape of the input is 100 multiple 100, and since it's a grayscale, so there's only one channel. And then that's it. There's only two outputs, yes and no. So this is the result. You can see how it learns, and it learns really fast. And this is the result of the 1000 times epoch. You can see the accuracy is actually at 98%, and I think it's high enough. So this is the progress. It's landing at this moment. And so we can say at the beginning it's almost 40%, and then it goes to the 19%, and now it's at 92%. So yeah, that's the basic idea about it. So Professor, do you got any question?
No, it's pretty clear. So it's 100 by 100 grayscale, and you use two convolutional neural layers. It was two class problem, correct?
Yep.
Okay. All right. And it does pretty well as expected. So are there any questions, guys? I think when they do these CT scans nowadays, they're three-dimensional. And so CNNs are still applicable, right? Because you can fit
Yeah.
in there,
Yeah.
not just a two-dimensional image. So something to consider. Okay. Any questions? All right. Thank you, Tianyan. Great job.
No, no problem.
All right. Who would like to go next?
I could go.
All right, Mitch, please right up there. Thank you.
Okay, so what I did, I was basically tasked with visualizing Word2Vec, and you'll see why. So what is Word2Vec? First, just so you guys give a little background, I know we briefly covered it. It's basically the vector representation of a word. So for this case, this is kind of example data of a picture I took. So that we give it a word this, and we give it an arbitrary dimension size. So in this case, it's 128. It's just too big to fit. So what these numbers mean, they're semantic relationship. So closer numbers between each word would have a more of a meaning across that dimension. So it's 128 dimensions, hard to visualize for us, three-dimensional human beings. So here's what happens, basically. So we get a word Paris, and then we get a word France. Those two words might appear closer to each other. London and England, those two words might appear closer to each other. So we can conclude that this axis, let's call it an x-axis, could be a city. And this y-axis could be a country. So now over here on this z-axis, I put Tesla and Elon. Those might not appear very close to Paris, France, and London, England. Now this is just a three-dimensional example. So in the 128 vector space, we'll have 128 more of these dimensions. So as you could kind of probably guess, it gets very hectic, almost impossible to visualize once you have all the data plotted. So the data that we used, I know we briefly talked about it in the most recent video. It was a collection of research papers about COVID-19. So there's 40,000 abstracts and another 10,000 full papers. There's the link if anyone wants to go to it. The code, I'll mainly just want to cover kind of key parts that I thought we should go over. So I tested this with TensorFlow 1.15 and 2.0, just slight changes to the code that were needed to be made for that. One of which is how you import the stuff for the visualization. I use TensorBoard, and TensorFlow 2.0 has static or eager execution, meaning you don't have to do a session.run to print out a variable or a tensor. So you can just print it out and it'll print out the way Python does. But I didn't. Some of the functionality of how we wrote the code for TensorFlow 1.15, didn't work with eager execution. So you can just go ahead and disable that. Another key part, this vocabulary size. So we set that to 70,000, meaning, so of all the data, we wanted to take the most common 70,000 words. So these are just, this section right here is just the initialization variables, basically, of what size of dimensions we want and so forth. So now to print out that file that looked like the word and then the 128 vector space, normally you would print out the vector space and add the word to it, and just get that in a file and then feed that into something to visualize it. But with TensorBoard, since it's built in with TensorFlow, you can give the name scope of the part that you want to do. So in this case, I named it embeddings. So this will carry the 128 dimensions vector space into basically a file format that's readable by TensorBoard. So when this runs, it creates the file. Well, it just creates the file in memory of embeddings. This section up here is the top right is the main loop. That was pretty kind of fairly standard stuff like have done throughout the semester. Key parts, once again, this line, this run metadata, that was for another TensorBoard object. So TensorBoard would take a metadata, which would be the word and the word count, basically the reverse dictionary, and the vector space, and that's how it computes along with other algorithms to show the data. So that was that. And this bottom part right here, this bottom right part, that's how you would configure the TensorBoard. So that's the standard stuff. This metadata.tsv, that was the metadata file that we had created from the main loop, and that was just the word and the word count. So basically the reverse dictionary. Just an example of what the reverse dictionary would look like. So it would have the word and then the associated word count. So in this case, viral, you could see was 23,532 and so forth. So to start the TensorBoard for the visualization, in the basic sense, when you install TensorFlow, I believe 1.15 or greater, TensorBoard gets installed with Anaconda. So when you install TensorFlow, TensorBoard will get installed. So this will already be there if you have, I believe, greater than 1.15. So what you want to do, that file that once it runs, it creates a directory that contains whatever, it's named whatever you want to name it in the code. And in that, it contains all the files that were needed, that were created for the TensorBoard visualization. So what you want to do, you start it locally by typing TensorBoard, and then you tell it the directory of the files that you made. So in this case, I named it corona_logs. Once it runs, I'll tell you what output, and then it opens up a port on localhost. So just a couple screenshots, I'll demo this. So this is what the data will look like. On the left here, you see, so this left here with the yellow dots, that's the data, 70,000 points of data, with each dot representing a specific word. Now, to break it down a bit more, I searched for the word coronavirus and isolated 116 points across, the 128 dimensions. So this is what it will look like, the 100 points. So the problem is with this, there's 3 axes only. Kind of hard to draw conclusions from just 3 axes when we're trying to represent 128 dimensions. Another thing you could do with TensorBoard is you could apply categorical coloring or clustering. So what that does, there's algorithms within the TensorBoard configuration to kind of see from the vector space what words might be associated with a specific category. So in the vector space, let's say you had a word that had in dimension 1, 1.10, another one 1.12. Those might be in a relative category. Default for this clustering was, I think, 50 unique characters, but I'll demo how you can change that in a bit. So once again, the limitations of this, there's only 3 dimensions shown for 128, or whatever arbitrary size you want. That kind of creates a problem or a difficulty trying to visualize, hey, this might be, some sort of relation or some sort of meaning. So just to show what technologies I tested it on, I used TensorFlow 1.15 and 2.1. TensorBoard, same versions, 1.15, 2.1. Both those got installed with the specific version of TensorFlow. I tested it on Ubuntu 16.04 and 18.04, which I'll demo on 18.04, and Python 3 was used. So let me switch over to the VM. So this is the data, all of the 70,000 points plotted across the 3 dimensions. So what we could do, so we can zoom in on this. I'll actually take so you could search for a word. So in this case, I'll just search for coronavirus, since that's what these papers were about. So you can take the neighbors, the nearest neighbors that you want. So we can have 100 up to, I believe, 1,000. So that's just calculate the cosine distance from the vector space of the actual word. So we can go ahead and isolate those just to show that it's a bit neater and a bit cleaner to see. So I went ahead and applied the categorical coloring. So now, to make that 2-dimensional image that we saw 3-dimensional, we can kind of now see that this dot right here, from the picture, kind of looked like it was flat, but now we could see that it's not. It has some sort of meaning across a different axis. Now, once again, the problem is this is only a 3D representation. This axis might not be clear. So to change these files to, it's kind of what I'm currently working on, to add more, to visualize this with more dimensions. So what you would have to do, you'd have to build the program from the source code, which is you'd have to download it from the GitHub and install it with something called Bazel. So basically what that looks like, once you install it with the Bazel, you get so you get all the configure files for TensorBoard. And then, so for this case, for the word embedding, so word2vec, it was in something called Projector, which is a plugin for TensorBoard. So if we want to go see those files, Projector, so we can go to Projector. And the files that were created started here. So we have the build, init, metadata, and so forth. I won't really go through those too much, but just to show you what some of the files, how many files there are. All these files have some sort of configuration for it. So it gets kind of complex. So to start this from source, we can go ahead and run this command, same command, but you're building it with Bazel. So basically, this whole directory that we downloaded from the GitHub, it runs it off of that. Now, when you install this with Anaconda, I couldn't find the same matching files as what was posted on the GitHub. So that folder VZ projector, the projector plugin, I couldn't find those to configure. So this led me to the idea that I needed to build it from source. So once we do that, we can go ahead and start it. Basically what's happening now, it's just, it contacts the server and it starts to build TensorFlow again, or TensorBoard. So once this will run, it takes a few moments. The same thing happens though. You point it to the same directory of where you had the files saved. Should be almost done. One thing I'd like to point out though, for some reason, and this was a new issue I discovered, it wouldn't run in Firefox. It would load, but it would be just a blank white screen. But when I took the same thing and ran it with this Chromium, which is essentially just a different version of Chrome, it ran successfully in that. So there might be something with the 1804, 1604 version of Firefox that's pre-installed that might cause issues. All right, so now this is started. Once again, go to the same port that opened up on localhost. One cool thing, so since the code, we talked about the computational graph. So within TensorBoard, when you have the configuration like I had it, this is essentially the computational graph that was created. So each of these has some sort of meaning, and it'll tell you what's created, the two tensors, and this will basically just visualize the computational graph, but onto the projector. So if you noticed, when I ran it just the first time, that was through Anaconda's build. But now, if you might notice what's a little different, I was able to add in more axes. So now, rather than just the standard 3, let me go ahead and apply the same coloring. So rather than have just the 3 axes, we now have, I believe, 11. So 4, 4, 3, yes, 11. So now this axis might represent something else. This axis, something else, and so forth. So this would be easier to, in my opinion, easier to see relations across the axes from, what the specific meaning might be. So for example, let's say this axis might be something with the virus, specific virus for the virus. So now we can add another axis here and so forth. So it's a little bit easier to visualize the 128 dimensions now, rather than just having the basic 3. We could change the algorithm of how it, I won't click these because the computer I'm using right now is not very strong. But basically these are the reduction algorithms, the compression of how it gets the data down into this 3-dimensional space, kind of like this. And then we could set a custom one. So we set the steps left and right of the words we want to count for semantic relation. We can manually set that if we want there. But now it defaults to 50 categorical coloring. Now I took it even further and was able to change it to 100. So basically now each color, it doubled what it might kind of cluster to. So you can have a bit more of a relation of what the color of the dot represents. But other than that, that is about it.
Really, really excellent work. Very well explained. So I'm going to open it up to the floor, but I have a couple of questions. So as you know, what we're trying to do is visualize this better. So you mentioned, you had a slide, something about the clustering algorithm, and then you showed this also of the 11 new features. So are those when you went to that folder in Basel, were those like scripts that were in there to convert the data?
Yeah, so I can go to that.
Because I guess my question is that what you're thinking about doing then? You're gonna add new scripts to this that would do, you know, kind of your own unique visualization.
Yeah, you could. I believe somewhere within them, I haven't found where, it computes the PCA, this TS&E, and the UMAP.
But this 11, how about, so these 11 that you're showing me, are they 11 from the 128, or are they new 11 that were kind of inferred?
Yeah, so they were, so when the data is compressed from the PCA, I can spherize it, so put it into basically a three-dimensional sphere. And with that, I added in the dimensions. So this is what was inferred from the PCA compression of 128.
Okay. All right. And then the coloring, that's one of those clustering algorithms, correct?
Yeah, I believe the clustering I saw, it was KNN is what kind of
Okay, all right. It does a
so that.
KN on the three-dimensional, and then it does a color.
Mm-hmm.
Okay, that makes sense. Yeah, so I think one possibility, obviously we need to discuss this further, but, you know, with, you know, Magash and everything, but one possibility is that you could just add your visualization scripts in there, right? And that's, you know, one possibility. But yeah, great, great, great. Can you, let's do an experiment here, if you don't mind. So apparently, from what I, you know, I'm sure everyone has read about this. This COVID-19 is doing some strange things, and one of the new developments is that it's causing strokes, and also that it does blood clotting. So I wonder if, you know, because, you know, if you look up like coronavirus, it's just going to say virus, you know, vaccine.
Right, right.
But if we look something a little bit more targeted, that's rare, it might be interesting to see what words. So, you know, for instance, if in the literature, the stroke, you know, stroke appeared, for instance.
Mm-hmm.
Is there any way for us to see, you know, let's say just like 20 or 30 words associated with that? Or?
Yep. So from the data, there's different variations of stroke, post-stroke, stroke with a period, stroke with a comma, and just stroke. So those
Let's
are all
just go with
different.
stroke, let's say, and then
We'll
see
do
if we
that.
can visualize just, you know, a few words, not that many.
Yeah, we'll set.
Just an
We'll
experiment.
we'll set that to 29, I believe. That's
Okay.
what that is. So what that is now, stroke would be right here. I can change this to have the actual words be shown. So stroke would be right here on this axis.
Mm-hmm. What are the words?
Basis. Actually, I might be able to show the name. So we got basis, Howard, emergency, lymphocytic, cat binding, hemorrhages.
You
So
know,
probably
what
brain
comes to
hemorrhages.
mind is that we could do as part of the visualization, instead of just showing the 72 closest words to stroke, maybe we could create like 3 clusters, and we say we pick stroke, and we want to know usually what like WebMD reports. So WebMD will report, what is it like? They'll report, you know, symptoms, remedies, side effects.
Mm-hmm.
So we could possibly then, the words that we show in green would only be medicine words. And then the words in blue would be only side effect words. And the words in, you know what I mean?
Yeah.
And the way to do that is, I guess we could have like a knowledge base. A knowledge base is usually a database where we have all this information. You know, all this information can be gotten from WebMD and we can scrape all that data. And so we could then look up things. For instance, we look at the closest 50,000 words. And out of those 50,000 words, there's these 117 that are medicine words. And then there's these, 300 that are side effects. And
Right.
that way, maybe we could visualize that. It's just an idea, something that occurred to me just now.
Yeah, it's just kind of replace some of the KNN stuff for the
Right,
coloring at least.
visualize specific categories of words associated with a sentence. And it's just something to try. Certainly that gives us a little bit more. It's not a visualization per se, as we've discussed, but it does give us a way of as I said, we can discuss, but it's an idea in this context. But yeah, great. I think this is really great job. I don't have any more questions. Guys, do you have any questions for Mitch? Go ahead, ask. This is one topic that I didn't have time to cover so much in class, but remember, as I said, this is one of those that can be pretty much a black box. You just give it the data and get excellent results like this. Or are there any questions? Mitch, is there anything you'd like to say?
Nope, I think I covered everything.
Yeah, all right, great. Yeah, excellent job. This looks great. So thank you very much. Virtual clapping here. So who would like to go next?
I can go next.
Okay, Drew. All right, go ahead, please.
So for the term project, I used the same dataset from the midterm exam. It is a dataset contains 5 species of flowers to recognize. So it's
Excuse me, Professor, I cannot see the screen.
oh. Right now?
Yeah, thank you.
Can you see the screen?
Yeah, thank you.
So this dataset contains 5 species of flowers to recognize and is for JPG format. But the dataset, the pictures inside is different sizes. So first I resized them to 28 by 28 by 3. It's a color image, so it's 28 by 28 by 3. And for the midterm, I tried all the other algorithms like neural nets, deep neural nets, and RNNs, and it gives me like nearly 63% accuracy. And that is probably because I reduced the size from like 320 by 200 to 28 by 28. So it lost a lot of features. So, and the picture is like this. Is some of them are for single flowers, and some of them are several flowers. So it's hard to recognize maybe. So the accuracy is pretty low. And this time I tried CNN for 28 by 28, and it gives me. And I tried different architectures, like 2 convolutional layers, 3 convolutional layers, and I tried different times. It gave me the best accuracy is nearly 43%. And so I reset the pictures to 100 by 100. And I also tried different architectures, and then it gives me the best accuracy is 54%. And I ran for like 14 hours. Is this one. And I also want to try to reduce the size to 150 by 150, but it's got memory issues, so I cannot run the code. And what is the problem is when I tried 28 by 28, the 2 convolutional layers gives me a better accuracy score than the 3 convolutional layers. So I guess it's not the more convolutional layers gives me the more accuracy score. That's it.
All right, great. So what did you say was the size that gave you the best results? The 100 by 100?
It's nearly 53%
That so
for 14 hours.
yeah, when you did, and that's when you had to kill it, correct? It's not that it finished. Did you?
Yeah.
Just you could have.
And that is probably because the data set is not that great to learn to recognize, because the flowers and it's not
Yeah, there's
like
a lot of variability in color.
Yeah. So, and that so
it's also, I should say, remember that the pictures, some of them are to the left, some of them have 3 flowers. Some, there's a lot of variability there.
Yeah, it's hard for the machine to learn to recognize the flowers, the species, but I could say that for the size, when the size is 28 by 28, the CNN gives me the best accuracy. It's 43. Then all the other algorithms is 33, and when the size is 100 by 100 is 53.
Okay, so 100 by 100 is the best.
Yeah, and I want to try more like 150, but I cannot run. It's called memory issues.
Yeah, so this kind of problem, I mean, this would require, this is, you need more iterations. How much data did you have in here?
I have 4,323 pictures.
Are they balanced? Is it a balanced data set?
Yeah, it's almost balanced.
Okay. All right. So we have that in your favor. Okay, and I see you said the best CNN was the 2 convolutional layers.
For the 28 by 28, the 2 convolutional layers gives me the best.
Okay.
Probably because there's not much pictures. I reduced so much, and
no, pretty good, very interesting. Are there any questions for Drew, guys?
For you.
No questions? All right, thank you very much. Great job.
Thank you.
All right, thank you. All right, so who would like to go next?
I can go, Professor.
Okay, please.
Can you see the screen?
Yes.
Okay. So, Professor, I used Kaggle dataset for the implementation of CNN algorithm, and this is my dataset for the scenery. These are the images for the scenery. It has buildings. It has the pictures of buildings and forest and mountain and sea. So there are 4 classes. The size of each image is, by default, it was 150 by 150. So I tried to run on it, but it was like having some memory issues. So I resized it. So I just changed the batch size and number of inputs. I changed resize is to 50 by 50 here, from 150 to, I tried at 80 by 80. So it was working fine. Here is the screenshot, but it suddenly stops after like few hours. I think it was some memory issue. It was on 76. So it stopped. Then I tried on 50 by 50 and it's working, but it's on 73. So I set it to number of epochs equals to 6,000, but it's working right now. I don't know where it will go. So uh, here I change resize my images, and then I change a little bit architecture. So and I used three convolution layers. Here I change the architecture by changing the dimensions. Of course, the 50 by 50 was max full till 13 by 13, and in the last layer it was 7 by 7 to 64. So currently this is the result for 50 by 50, and that was for uh, 80 by 80 into 3, but that stopped due to some issue. Yeah, that's also accuracy is 76%, precision is 76, because 76.5, and F measure 76.4. That's all, Rohit. Any questions?
Right. Great. So how many, can you give us information on the data set? How many samples, how many classes, was it balanced?
Yeah, so dataset has 4 classes: buildings, forest, mountain, and sea, and each image is in PNG format and has 150 by 150 size. And I used number of epochs equals to 6,000, where I put the batch size equals to 100.
How many samples do you have per class?
Samples, okay. So around 800 in one folder, like 841, 700, 800, 900, like that.
Okay, so they were all around 1,000?
No, approximately 1, 2, 3, 4. I think around less than 5,000 and above than 4,500, like that.
Okay, and each had about 1,000 samples.
Yeah. Okay, so what you're saying that I should have 1,000 samples in each folder?
No, I'm just saying it should be balanced. That's why I was asking. Okay.
Oh, no, not, they are not balanced. A little bit, they are different, little bit like this is.
Well, I
800.
mean, if the difference is like 800 on one and 900 on the other, and even 600 on another, I mean, that's fine. That's balanced.
Just like this is 777.
Yeah, that's
and that
fine.
was
Imbalance would be if in one you had 777 and in the other one you have 30. That's imbalance.
Okay. So if I have the same number of
Yeah,
samples.
no, that's fine. That's balance. I mean, that little difference doesn't matter.
Yeah.
Okay, yeah, so it's a balanced data set. So that's good.
Mhm.
Back to the code. Let's take a look at it.
Yeah.
All right, scroll to the where you read the data.
Okay. Here?
Is that where you read the data? So you have 4 classes, right?
Yeah.
Can you do that?
Here. And then I just read the data as you read it.
That's forest. Where's the other 3?
Yeah.
Where?
Yeah, I'm showing it. This is class 0, this is class 1, this is buildings,
Okay.
this is mountain. Yeah.
Keep going. Okay, great. Yeah, so that's good. Can you go to the inference function?
Yeah.
Okay, there, yeah.
Yeah. This I use this one. So
You use that one?
yeah.
So you use 3 convolutions.
Yes.
Okay. Did you try with just convolutions to see which one was better?
Yeah, but that result was very bad, like around 40%.
Okay, so 3 convolutions was better for you.
Yeah.
Yeah, that you know, that's one thing. If you notice in the course, we've always done a lot of deep learning layers, and usually fewer is better. But with convolutions, it's odd. It's, you know, a little bit more might give you better performance, and I think it's just that you have more filters, and these filters do a better job at finding things. So certainly CNNs, you know, one thing I want to stress, and I think like Sumendra mentioned this with his autoencoder, is he still would like to add some convolutions in there. And so just
Yeah.
keep that in mind, you know, for all your projects, see if you can somehow add convolution, even if it's unsupervised somehow, see if you can add convolutions, because they seem to have this additional power with these filters of just learning things a little bit better, more precise. But yeah, okay, all right. Good job, Sharak. Right?
Yeah. Thank you, sir.
Yeah, so are there any questions for him? Guys, any questions? So what were your classes? What else? Mountains, right?
Yeah.
And they were
Mountains,
colored.
sea, buildings. Yeah, all the color images.
All right, great
Yeah.
job. Thank you very much. Okay,
Yeah.
so who do we have next? Okay.
Me, Professor.
Okay, go ahead, please. Relian.
I see. Can you see?
Yes, we can see your screen.
Maybe share nothing. Maybe I change another screen. It's here. So my task is to generate. My task is generate tasks, and I wanna use the dialogues to create. Suppose there is a question, I give an answer, and that is my task. So I select the dataset here, and could you hear me? This is the dataset, and this is the example. This is a CSV file, and it has each lines, which means in this cartoon, we can see Stan says, you guys, shift is going away, and Calix says going away. For how long? I suppose that this is the question and this is answer, and then this is the question, this is answer, and so we can have many dialogues. And then I tried RNNs at first, but I have a problem. It's just for example, so maybe let's focus on the pre-process first. First, I read the CSV files to lines, and then I clean the data. There's many. I just clean the data. For example, the SI2 is, so I just process some abbreviations. Maybe I convert them to I'm to I am, his to his, for example, and then I want to find the appropriate sentence, because we have to define
just, for example, there is a question, there is an answer, and we have to define how the length of the question and the length of the answer, and we have to, for example, in this example, you guys, Chief is going away. This is 11, 11 words, including the punctuations. Yes, this is 11 words, and then I use the code to determine that I just think that 30 is a good number because we can cover more than 80% of the sentences, and finally I choose the length of a sentence is 30, and then I create the frequency of vocabulary, and I set the threshold to 3, and if the frequency is less than 3, I will set that to unknown, and then I create the vocabulary dictionary. And I also add the pad and the end of sentence and unknown and go. And if a word is less than 3 times, it will be set the unknown. And each time when there's a end of the sentence, I will say there's an end of sentence. And especially when, for example, here, this line only has 11 words, so I will pad 19 times, just pad until it is 30. Yes, the length is 30. So now we have all the X is or the data X contains 30 words, and well, I choose the length as 30,000. Yes, I choose 30,000 sentences, and you can see. Oh well. Yes, here. So finally, we can convert the text to integers, and there are 26,000 sentences we can use, and then at this point we have all the text to integers, and well, we have 2 dictionary. One is the dictionary which is vocabulary to int, and another is int to vocabulary. And this is all the pre-process. I also set the value set, and I pad the sentence. But I want to use the RNN, but I have a question. I just so the input is 30 and the output is 30, but in class we only learn the input is 30 words, but the output is classification. So there's only, just one output. So, I tried to write the difficulty is the infer. So I finally choose the sequence to sequence model, and I can, I also combine RNN, but I combine word embeddings, and sequence to sequence is just a better model of LSTM. It has first it converts all the words to the matrix in the word embedding, and then we use the bidirectional RNN, and finally we convert the matrix to the result in the decoder layer, and and more
more specifically, it also combines the attention model. Yes, and that is what is special in this model. And the results are, I tried several different parameters. One is 64 encoder by RNN and decoder. And you can see here some examples. For example, guys, oh no, this is just the output. This is my, you can see it here. Well, this is some of my training training log, and the validation loss ends in the 1.747. No, that is not the best. It is the 1.744. Yes, and at this time, we can see it is not a very good robot, but it is we can see that it is a basic robot. Well, here's some of the examples. For example, it inputs, well, these inputs are generated by the sentence given, I mean the data. This is the data, and this is the results the model generates. Yes. For example, we can even generate now. I will use another screen. For example, this is my task file. I load the checkpoint here. I load the sorry, let me find checkpoint. Well, here it is here. I will save the best checkpoint, and I load the checkpoint here, and now I could we could just say what we want here. Maybe we can say hello. We can say hello, and we could run the test file, and you can see what is the results. It may take some time. Oh, it is not a good, but we can see that the robot now is not so robust. For example, it says, "Oh God," and O is 101, and God is, and this is its task generated, and this is just random task from the data set. I could make them output 30 times, and we can see that it is not so much robust robot, because sometimes it just says end of sentence, and another times it says the repeated word again and again. Let me share another screen. It is still here. It is still here. Here is some records. Here is some output record, and we can see that it just repeats the same words again and again. But sometimes you can see if we change the input, it may say something. we can see this word is different, but then it generates the same. I'm gonna to get a. So the first words are different, but then may repeat and repeat. And if I change the parameter, I also tried. I use the parameter 64, and if I use the parameter 32, this is the 64. If I use the parameter 34, we can see 32 is no better than 64. We can remember the 64 is 1.744, and this is 1.8. So that is no better than that. And at this time, it is good at speaking. I'm not have to get. I'm not gonna to get. I think that is maybe the gradient may end up in maybe it end in not in global best. It's just in the local best. So we repeat the same words again and again. And finally, so that is my shortage, and the robot is not so robust. And maybe the game would perform better, but last semester I tried games. Some games would repeat another words again and again. So maybe this is my final project. Could you hear me?
Yeah, great. Yeah, great. So I have a few questions.
Yeah.
So one of the things, so there's several things that I noticed here. So you said you were using sequence to sequence.
Yes, right.
So I got this straight. Your idea was, and you said you use padding and you use input sequences of 30 tokens, 30 words.
Yes, 30, yes.
Okay. So your idea is you feed it 30 words and then it should output 30 words, correct?
Yeah, right.
Okay, and so the initial 30 inputs are like, hey, how are you today? The weather's great. What do you plan for tonight? And then you expect then the RNN to say, well, I'm gonna go to the movies and then this and that.
Yeah.
And so it seems to me that that's a very difficult problem for several reasons. One of them is sequence to sequence. I think, a classic example of it is translation. But when you have translation from one language to another, let's say English to Spanish or vice versa, the sequence of the words, it's similar. You say the car or the cat, and you're going to say that same word in the other language somewhere around in that the input word. So the output word is going to be sort of in the same sequence. So a bit of sequence is maintained. But here, you're saying something, and the answer could be just about anything. What are you going to do today? Well, you're speaking to a person that likes sports. They're going to say, I'm going to go play sports. You're talking to a person that likes to read. They're going to say, I'm going to read a book, and so on. So it's the possibility is that it could be, the possibility of answers is just that much larger. So I understand what you're doing. I'm not saying it's wrong or right. I'm saying it's more challenging, right? For what you're saying.
Right.
I have a feeling that maybe predicting the next word in the sequence and building an answer based on that, might be a little bit more useful. Also, your sequences of 30 words. Why 30 words? That seems like very long. I think most of your words would probably end up being padded anyway.
Yeah, right.
Most of your sentences, I mean, you know, so I think definitely something shorter, right? You should have, you know, like five words, 5, 6, that's usually enough to convey some meaning in there. So certainly those two observations I would make. How much data that you have, because, you know, you're really
30,000.
yeah, so 30,000 to learn how people in that show, South Park, you know, how it's not enough. I mean, for such a, you know, such a large possibility of things they can say, I think. So certainly, I think this goes back to what I said about n-grams. You know, it's more likely that you're going to find n-grams of 2 than you're going to find n-grams of 5 or 10. And I you know, and I think the same principle applies to here to RNN, right? It's not, you know, learning those some of those sequences they may only see once. They might see sequences of 2 and 3 a little bit more often, but, you know, so the longer you make them, the more challenging it will.
Yeah, that's
I would certainly advise.
Initially, I just thought that maybe word embedding would help the machine know.
But what do you mean by word embedding? That I don't understand. I think you just mean that you're vectorizing the words, right? But you're just using integers. I think I saw if in one of your let's go down to where you have 2 sentences as a list of integers. Can you go down to that? That's where you show 2 sentences and you show them as a list of integers. Further down.
Yeah, but it has an encoder layer.
Oh, no.
So
Just go down.
yeah.
Further down. You have somewhere okay, there. Okay, so if I understand this correctly, correct me if I'm wrong. Your RNN, you know, that input 3 where it says word IDs, that's the input, correct? And then the output that you get from the RNN is response 3 word IDs and those 3 integers that you get there. Is that what you're getting?
In this model, it contains a encoder layer and a decoder layer. So I thought maybe, and it also has word embeddings in that layer, in the encoder layer. So
I'm not sure I understand what you mean by that. The RNN would be input, so that, you know, they're one hot encoded basically there. So can you show in the code what you mean by the word embeddings and the other thing you mentioned?
Sure, another. Yes, it is here.
Mm-hmm.
And when so basically this layer contains encoder layer, and then it will goes to the decoder layer, and it is in the encoder layer. It will there's a word embedding or something. Because to my understanding, at first maybe the integers goes into the encoder layer, and in this layer is transmitted to the another matrix, and then it may, for example, it may learn the relationship between the king and queen. I understand that way, and then finally it will go through the decoder layer, and the matrix will finally go to the integers.
I'm not clear really what you just said, but so, you have to feed it some kind of a vector. Do you know the size initially of the vectors that are fed? They're one-hot encoded vectors, so all the words. What was the size of your vocabulary?
Yes, it's in the. Let me check. It should be. Where it should be. The size of a vocabulary is 14,000.
Okay, 14,000. So.
And after deleted the times less than 3, we only have 5,000 words.
Okay, so let's say that your vocabulary size that you're using is 5,000. So you have sequences of 30 vectors of input that give you sequences of 30 vectors of output, and where each vector would possibly be of size 5,000, but only the integers are used there. I don't know if for both inputs and outputs. Now, what I believe you mean when you say that then it goes through word2vec and autoencoders might be that the vectors, before they go into the RNN, go from a one-hot encoded vector of 5,000 to maybe a vector of 128 because it goes through some kind of word2vec operation.
Yeah.
That is what is used in the RNN, and therefore that might help you with compression. That's how what I would understand, and then somehow you have to decompress it at the end. Do you understand what I'm saying, Rillian?
Yeah.
So is that what's happening?
Yeah, I guess that I know. You mean that because the ones I input are integers?
Well, I'm asking, so, I think I've said this many times in the class. So this is a problem when you grab some code online and you kind of just use that instead of building your own from scratch. So you end up not being clear about certain parts of the code, right? And so this, this is the problem. And then now you're not sure what's going on with the vectors. This is very important, right? That you should always know when you write your code that you're exactly clear. Okay, these are my inputs. This is the size of my vectors. If you tell me that you're using some kind of word2vec or encoding mechanism, that has to be clear, right? And so you must always have your dimension, and the way to be sure about that is to know your dimensions. You understand?
Okay.
Right?
Okay.
So, would you like to summarize before I open it up to questions from the audience?
Maybe no.
Not summarize? Okay, so yeah, so I think that's, and I haven't read your code, but I feel that's probably what might be happening is when you say you're encoding, it says create an encoding layer there. And if it's a process before feeding to the RNN, you may just be, it makes sense that you might try to shrink a one-hot encoded vector from 5,000 to something a bit smaller. So that's certainly something that people do. Okay, all right, so that's all the questions from me. Are there any questions from anyone else in the audience, guys, in the class? Are there any questions? All right, no questions. Okay, so, I want to tell you guys that I really, really enjoyed your presentations. So they were so good. What amazing work you did. So thank you very much. Very interesting ideas. I hope this has been helpful to you, and that you continue, you become, deep learning ninjas. All right, so that's it for me. We're done with the semester. I really don't have, there's no more time for any new topics. I appreciate Mitch's discussion of Word2Vec. I thought it was pretty thorough. So, you know, and then we'll be posting the code. If Mitch can send us that COVID Excel spreadsheet that he used for the text, I can post that on my GitHub, and then that way it doesn't have the JSON in there. So it's certainly something a little bit cleaner that you guys can use. So Mitch, if you're listening, if you might send that to me, I can post it on the GitHub for anyone that wants to try it. So, you know, I want to again summarize. You know, we covered all the important topics. I'm going to say even Word2Vec, except we didn't get a chance to cover really reinforcement learning. So GANs, for some of you, we covered in 520. If you haven't taken 520, I may just cover it there. So, and I might actually, reinforcement learning could find its way into 520. And it's not technically deep learning, so it could end up there. Otherwise, if you're interested in any additional topics, you know, we can always talk about an independent study. All right, so that's pretty much it for me. Okay, again, really great job. I will be posting this video later, so you guys can look it over if you want any details. And then otherwise, please, I will create a Dropbox for you to submit all these materials, right? I will be sending you some emails, and then also please don't forget that your final exam, let me look that up. Okay, so your final exam is, let's see, the class is Tuesday. So Tuesday and Thursday starts at noon, correct? So Tuesday at noon. Therefore, our final exam will be Tuesday from 12:30 to 2:30. It'll be a written exam online. All right, are there any questions before we sign off?
Nope.
No questions. All right, great. Thank you very much, guys. And I'll see you on the day of the final.
Professor,
Sure.
what will you going to ask in the exam? It will be MCQs based or programming based?
It'll be, it's comprehensive. So it's a written exam about, you know, between 6 and 10 questions. And it's a written exam, obviously online now. But it could be code. It could be explain, could be questions about the presentations. I mean, anything, just to test your understanding of deep learning.
Okay.
Or I might give you a problem and say, select the most appropriate algorithm for this task. You know, and you have to describe how you would do it. You know, I want to see usually the things that I want to see are the features and the dimensions. So those are the key things that you own that whenever you do a deep learning algorithm. You own your inputs, your data, your and the dimensions of the architecture. Right?
Yeah.
All right. Yeah, that's what you can expect. Any other questions?
Yes, sir. Actually, I have a question.
Yes, sir. Go ahead.
Because in class, you in the code example, you for example, you use 3 words, and in RNN code, RNN NLP code, you use 3 words to find what will be the next word, right?
Okay.
And at this point, maybe the input is array with 3, and the output is actually the classification of Y, right?
Sure. One word predicted. It was a vector.
Yeah.
It was a one hot encoded vector.
Yeah, and the loss is the I remember is the reduced mean, and we can calculate the cost. But actually, in my project, for example, when I want to input a array of 30, and the output is also 30, and how could I calculate the loss?
Yeah,
cost.
so in that, and if you want to use the code that we had in class, you know, you could predict, if you notice in the code, there's a little place where there's, you grab a -1, and it just means you grab the last one of the outputs. So instead, you would want to grab more than just the last one. Do you understand what I mean?
Not so much.
Okay, let me go to the GitHub. I'll show you. If I go to the GitHub, let me share this. Can you see my the website?
Yeah.
Okay, so if you go to the GitHub, and then this is RNN's NLP.
Yeah.
All right, so this is the code that we discussed in the class.
Yeah.
And if you look here in the inference function, which is this one, RNN NLP, you see this? You get outputs, right?
Yeah.
Yes?
Yeah.
And then you can see here there are n outputs, but we only want the last output. Therefore, notice that this is only the last one. So you actually just get, instead of getting, all of them are here, but you only intentionally grab the last one. So you would have to do something here to say, you know, that I want actually more than just the last one.
And is the loss function the same?
The loss function is the same. That wouldn't change.
Oh, maybe I'll try again because I have difficulties writing this part.
Yeah. No, well, I mean, yeah, that's what you chose to do. So, you know, it's going to be challenging, right? So one, you know, you can do that. Remember, this generated sentences. So you could give it, you know, certainly don't try 30, you know, try 3, you know, 4 or 5 at most. That generates one predicted word. And then you could use that predicted word to kind of infer the next word and the next word and so on. And, you know, the problem that you chose is difficult. I mean, you have one question and then you want an answer. You see, so it might be easier just to generate bigrams. You know, I got 2 inputs and I get another output. And from that output, then I generate the next output and so on. But as far as being able to I understand your question. So you have 3 inputs, you want more than 1 output, that's this right here. Okay, and then here you're slicing, and you can see that it's written there. We only want the last output. So that's why you end up slicing it by -1.
Okay.
All right?
Yeah, I'll try again.
All right, good. All right, so are there any other questions? Okay, no questions. All right, great. Guys, again, you know, I really enjoyed your presentations. I've taught this class many times, and I think this was one of the best set of presentations. So really great job. Okay, and so don't forget the exam on the date I gave you on Tuesday. So I'll see you guys. Don't forget to submit the materials, and I will see you, or I guess online, you will do your exam in a week. Okay, I will also send you some emails, so look out for those as well. All right, thank you, and have a good day.